Welcome along to another video on gravity. So there's a more comprehensive video already on the YouTube channel, so just watch that if you need to go over the basics like the equations, how to find the energy to move between two locations in orbits or how orbits work. But there are three things that crop up in this week's past paperwork which I thought that were worth tackling. How to relate density to the gravitational field strength of a planet or of their object. How does the force of gravity or the field strength or even the potential vary between two objects? And then finally, how do we get to far, far away, or probably more properly, how do we calculate escape velocity? So we know that G is equal to Gm over r squared, but we also know that the mass of an object is its density times its volume. All the objects we're interested in relation to gravity are spheres, so we know the volume of a sphere is 4/3 pi r cubed. So the mass of our planet or other object is rho 4/3 pi r cubed. So we put that back into this equation. We've got G over r squared times rho 4/3 pi r cubed. And then that would mean that the r squared, cancel that down to a single r. So G is, we'll just do all the constants first. G 4/3 and pi rho r. And that is in one of the questions you'll be tackling this week. But that relationship, G is proportional to rho density times r, has cropped up in quite a lot of multiple choice questions. And once you understand it, it's much simpler to do your question. So if on a certain planet, density rho, radius r, we have a field strength G, what would the field strength be on a planet made out of material 3 times the density, twice the radius? So that's just 6 rho r. So you get 6 times the field strength. Now let's have a look. Let's just imagine we've got, usually we think about the Earth and the Moon. And we imagine a kind of line connecting their centres. And first of all, we're going to think about G, the field strength. There's a slight complication coming up about the best way to write this. But we know, keeping it simple to start with, down here on the Earth, the effect of the Moon is pretty minimal. So it's going to be 9.81 on the Moon, on the Earth. And yeah, there is a bit of a pull from the Moon. It affects tides and things, but it keeps, that value doesn't really change. On the surface of the Moon, it's about a sixth because of the Earth, because it's a smaller object with less mass pulling us down. And we can imagine a point somewhere in between where the field strength is 0, the balance of the pull of the Earth and the pull of the Moon exactly balance. So how might that look as a graph? I think it does depend on whether the question says the magnitude of the field strength or we're about giving some allowance for direction, because you can see the field strength here is in one direction and here is the other direction. So let's do allowing for direction to start with. So I think we'd usually consider G on Earth to be a positive number. So the line starts at plus 9.81. We know it hits 0 at some point, and then about 6 times less in the other direction. So we get pretty much a 1 over r squared graph, pretty minimal in between and going the other way. If they're just after magnitude, then we would just swing up. Well, I wanted to do that in another colour, back to on the Earth, but again that's about the 6th. So the blue line is just if you're referring to magnitude. What about potential? Well, potential are scalars. So remember, it's minus Gm over r. So it's always negative, it's a scalar, so we're just going to add up the two negative numbers. We're never going to get a 0 point. I think I'll just redraw the diagram. So here's the Earth, here's the Moon. And then let's have a... So we know again the line starts on the surface of the Earth at minus 63 megajoules per kilogram. And then on the moon it will be negative, but much less negative. And there will be a point somewhere in between where it would be easiest to escape. So that's a kind of 1 over r type graph over here, and a 1 over r type graph over here, and then a kind of area in the middle where it would be considerably easier to remove the object, so it's getting quite close to the 0 line, even though it'd still be negative. And then finally, we can start thinking about escape velocity. It's easier to think about the moon because it gets more complicated if we start thinking about air resistance. But the basic idea is that when something goes in the air, obviously the whole point of the moon is it doesn't go in the air. When you throw something upwards in a vacuum, the kinetic energy turns to potential energy. When we get to 0 kinetic energy, it turns around and comes back, and that's how we do with kind of projectile motion on Earth. But we now know that there's if we ever got it all the way out to where EP is 0, or potential is 0, then we would escape forever. So if we can get out to far, far away, and to do that, our kinetic energy to just get there would need to be the same as our potential energy, or the same magnitude as our potential energy. Our potential energy is the potential, that's the energy per kilogram, times by the mass, little m, of the object we're moving. And remembering V is minus gm over r, so we've got a half mv squared. Remember, I've got my magnitude here is equal to gm m over r. Looks like our little m's are going to cancel, and that's because the escape velocity is the same for objects of any mass. And so we get v squared equals 2 gm over r, or v equals the square root of 2 gm over r. But the key thing is we do need to remember, because I have seen it asked where they didn't ask for the equation, they merely asked if an object's got a certain amount of kinetic energy, looking at a graph, would it escape? It's whether the kinetic energy, if added to the potential energy, that's quite a good way. So it will escape. The potential energy as a minus number plus the kinetic energy as a positive number is greater or equal to 0. Hope you found that useful, and I'll upload it now.